I mean, sine rule is terrific, but sometimes we don't have the information that we need. So a cosine rule can come in handy. Let's create it. Again, we'll draw in a perpendicular. Now, this time I'm going to play with Pythagoras. I could say that h squared is equal to b squared, and I'll just call this little bit x. So b squared minus x squared. But if I did the other triangle, then it would be c squared is equal to h squared plus, well, it'd be a minus that little bit that I called x. Again, let's eliminate the parameter. I end up with c squared equals b squared minus x squared plus a squared minus 2ax plus x squared. Well, hang on, things cancel there. I now have b squared plus a squared minus 2ax. But if I now look at this right angle triangle, I can play around with that and I get actually x is b cos c. Substitute that in and there I have it. All the cosine rule is really is Pythagoras' theorem, but it's just taking into account that it's not a right angle triangle, because of course if it was a right angle triangle it would be minus 2ab the cosine of 90, and the cosine of 90 is 0. It disappears. So it really is just Pythagoras' theorem. Again, I did it for the angle C. I could have just as easily had a squared is b squared plus c squared minus 2bc cos a, and so on and so on. Do some quick examples. So we want to find t squared in this case is f squared plus m squared minus 2fm cos t. Substitute in. Now this is the one where you've got to be careful. It's really easy to make a quick silly mistake, because remember that's t squared. So remember to find the square root of the number to get the actual length. In this case I've done it to the nearest whole number. Find an angle. Some people just remember the one formula and then rearrange it and get it and make cos f the subject. Some people just remember cos f equals, remember that, it doesn't really matter. I mean, up to you how you prefer to remember the formula. Let's substitute in, and of course the nice thing about the cosine ratio is we don't have that issue, because of course obtuse angles with cosine are negative. So the calculator will know straight away, oh well, you're talking about the obtuse angle, you're talking about the acute angle, depending on whether it was a positive number or a negative number. What about a question like this though? Okay, I want to find b. Right, let's use the sine rule. Oh, hang on, I've only got one angle. No good. Let's use the cosine rule. Oh, hang on, the angle's not opposite the side I'm trying to find. That's okay. We can still use the cosine rule. A is the angle I've got, so I'm going to assume it's for finding a. So a squared is b squared plus c squared minus 2bc cos a, and if I substitute in the information, I can still go and find b. I've just got to rearrange this and make b the subject. I end up with a quadratic though. Off the top of your head, what multiplies together give 40, what adds together give 14 cos 25? No, of course not. Let's put it into the quadratic formula and we get this lovely expression. And unfortunately, unless they give me more information, I come up with two possibilities, because actually there are two different triangles that you could create with those dimensions, and one of them would have a side where b is 5.85 and the other triangle would be where b is 6.85. So there actually is two possible answers for b. And as I say, unless they gave us more information, we can't really work out which one of those two it is. Let's do a 3D trig one, and this one comes from quite a few years ago now, 2003 extension one. David's in a life raft, Anna is in a cabin cruiser, and she's looking for him. Where's David? They're in contact by mobile phone. David tells Anna, who's decided to change how she spells her name, that he can see Mount Hope. There's Mount Hope over there. Now, fortunately, David has one of those, what do they call them, theodolites or something that measures angles. Wow, that was lucky on that life raft. He had one of those. And he says that, oh look, Mount Hope, it's a bearing of 190 degrees, and I can see that the angle of elevation is 16 degrees. Well, fortunately Anna also has the same equipment on the cabin cruiser and goes, hey, that's funny, from me the bearing's 139 degrees and the mountain's got an angle of elevation 23 degrees. But they also happen to know that Mount Hope is 1,500 metres above sea level. Whew, how lucky were they? Now we can find the distance and the bearing, and Anna will know where to go and rescue David in his life raft. See, this is why we need to know our maths, because you never know when that sort of situation will arise. Here's our diagram. Let's put it all together. Let's find some triangles. Let's create two-dimensional triangles, because it's a lot easier to look at than three-dimensional triangles. So we had this one for David, the 16 degrees angle of elevation. There's Anna's triangle, 23 degrees. We also got some information about the bearing and all these things. So bearing 109 degrees, and Anna over there, it's 139 degrees, creating this lovely triangle. So we want to find the bearing, so it'll be that one I've marked in green, and the length, the distance, how far are we going to go and get them. Okay, from one of those triangles, which one? The first triangle. BD over 1500 is tan 74, I know that. I now have an expression for BD. I could do something similar. Now, when you're doing your working out, it's perfectly fine to do something like this. If what you're doing is exactly the same steps, it just happens to be for different numbers, rather than putting all the working out down, you can go, oh look, similarly AB will work out to be this. That's fine. Let's label that on our diagram. We now have two sides. What can we use? Can we get some angles in there? Hang on, I'll draw in another compass over there at B. Now, bit of geometry. I can now look at all these and say, hang on a sec, NDB, that angle with DB, what I labelled as N double dash, that new compass I was drawing in, they're co-interior angles. I know they add up to 180 degrees. I now know DBN double dash is 71. I could do a similar thing. I could play with geometry and show that ABN is 41. Now I can work out ABD. Yeah, right, well that's really the same angle, so if I subtract that, I end up with ABD is 30 degrees. Bang, let's put that in our diagram. We should now be able to find something. What could we work out from that? Can I use the sine rule or the cosine rule? I can use the cosine rule. I want to find B, I know the angle opposite to it, and I know the other two sides. Okay, throw it into the cosine rule. Whew, just chuck it all in the calculator. Okay, making sure we're pressing the keys right, because there's a lot of different functions we're using there. We end up with 2,799 to the nearest metre. Okay, we know how far apart. Now we've got to find that bearing. We've got to find an angle. Wow, ideally, if we could find that angle, it would be nice. Sine rule. Sine of DOB over 1500 tan of 74 is sine of 30 over B. I didn't write 2799 because that was an approximation. So whatever number that is, if it was the last number I used, it's just going to be an answer button. Otherwise, I could store it in the memory rather than typing the whole thing out again. The sine DAB is that. Plug it in. But is it acute or is it obtuse? It might be one or the other. What would make sense? Well, let's assume it's the acute one. Now, if that's true, then BDA would work out to be 80 degrees 51. But hang on, when I look at the length of the sides, the DAB has to be bigger than angle BDA. So it can't be that one. Therefore, it must be the obtuse angle. And in that particular year for the HSC, when that question was in, you better believe there was a lot of people that just assumed it was the acute, because that's what my calculator told me. Didn't even consider that it might have been the obtuse one, and obviously then ended up with the wrong answer. So we now know that that angle there is 110.51. I can now work out the bearing, because all I got to do is add it on to the 139 we already knew, and that will give us our bearing. 249.51. We got it. Whew. Alrighty, let's play.